Swayam Prabha. Digital India. Educated India.
Hi, welcome back to Mechanics and Control of Robotic Manipulator. In the last lecture we have seen cascaded design. Last class we have seen how to simulate you can say dynamic control of you can say robotic manipulator using joint space. So this particular lecture is actually like in addition to that, because last lecture or you can say last simulation itself I said the task space I did not include it here. So this particular lecture is actually like towards task space. So in the sense inverse dynamics in task space and the all motion control, which is actually like which includes computer torque control or PD or PID. So these all we would be seeing. In addition to that, we have attempted the cascaded, which we call integrated backstepping or simply backstepping control or dual loop control. That is also we are going to see in this particular short video. So in that sense, we are actually like trying to see what is inverse dynamics in task space. So then we would be going like how we can modify the computer torque control when we require the task space variable or the you can say desired variable. So similar way we can see the motion based control, which we call like PD and PID control, and then we will go to the dual loop or double loop or cascaded or backstepping control. So in that sense we will actually like take the same scenario what we have seen in the dynamic control of you can say joint space. So only thing here I would be trying to show a small tricky one, because so there we have seen like if the theta 1 desired and theta 2 desired is given as a profile, how we can do it. So instead of this, so I am trying to show a circular profile in task space, how that would be followed. This is one of the common you can say practice used to do for the control performance of any system. So in that sense we are trying to see that way. So now we will talk about the first thing is inverse dynamic simulation. So of straight away like we talk about to our serial planar parallel you can say planar serial manipulator. So in the sense we will talk about the Euler integration parameter, then the mass of link 1, link 2 and the link length and the gravity. Again, since we are talking about inverse dynamics, the gravity would be playing a different role, and most of the common manipulators are gravity balanced, so we assume that zero gravity here. So we will come back later on. So if we make it 0 instead of 0, if we put it some gravity value as 9.81, what would happen? Okay. So in that case we are actually like talking about the circular profile. So if you look at it here, the link length is actually like 0.5 and 0.4. So I am trying to see that 0.4 is the radius both x and y. 0.4 by 0.4 is the center, and 0.3 radius as a circle I am trying to draw. So in that sense the mu desired is actually like coming in this way. Okay. In addition to that, it is actually like 0.2 times of t, in the sense it is omega t theta I can write as omega t, where omega is 0.2. Okay. So now based on that you can actually like take a time derivative, that would be mu dot desired, then further you take the second derivative, that would be you can say mu double dot desired. So these are actually like we have actually like used. So in the last joint space we have seen how the cubic polynomial can be used, but here even without cubic polynomial how the circular profile can be generated, that is what we have seen here. So further what we can see, once you know this, so we are trying to find the inverse kinematic, so that just for our own reference we try to find out what would be the q desired and what would be the q dot desired. Okay. So once we obtain this, then we are actually going back to the initial condition. Since the initial condition supposed to be same for the actual desired actual and desired the initial condition, so we are actually like using it this condition. So instead of actually like deriving it directly, so whatever the desired the first value we are actually like equating to the q and q dot. So in the sense your initial condition defined as here. So after that we are going for the dynamic terms, since it's a inverse dynamics, so we are trying to find out the desired dynamic term, in the sense inertia matrix based on the desired value. Similarly, other effects due to the desired value and gravity due to the desired value we calculated. Similarly, the actual value for the simulation. In the real time we don't require this, but we are doing the simulation, we need to find out the actual inertia matrix, other effects and the gravity. Now based on this we can actually like use the what you call you call subfunctions. So we can use the inertia subfunction, then the other effect subfunction, the gravity effect subfunction. These all we have derived in the last you can say class itself. So then this is the Jacobian, because here Jacobian is required, forward kinematics and inverse kinematics are required, so we can use it this. So based on that we come back what you call one additional variable which is j dot, because you know like so q double dot desired can be derived in that way. For example, you take mu dot equal to j of q into q dot. So then you can see like mu double dot can be written as, so j of q into q double dot plus j dot into q dot. So in the sense the j dot is required, so we have derived the j dot based on the time derivative, and then actually like we got this additional subfunction. Once we did the subfunction, this is the inverse dynamic model. So where m of mu into mu desired double dot plus n of mu comma mu, like a mu desired comma mu desired dot. So this is actually like we use as a f, but you know like f we can write as tau. So in the sense tau is j transpose of f, that is what we are going to use. So in the sense this is the inverse dynamics. So where first we calculate the you can say the end effector forces and moments based on the known model, then this is the you can say inverse dynamic you can say model in input vector in task space, that we convert it into joint space, because so the original system would be derived based on the joint space because the actuator fixed on the joint, right. So then we derived this. So we are actually like trying to use the simple you can say Euler integration, where the velocity propagation and the position update, and then once you update then you do the forward kinematics just for animation. So then you can see like then you can actually like see in the Matlab code. So I just want to show that this is the inverse dynamics model which we derived in the Matlab. You can see these are the cases which we have seen in the you can say earlier slides. So now this is the desired value, and then this is the joint desired value just for our reference, and this is the initial condition, and this is the dynamics. So we have derived actual and you can say desired dynamics. Then this is the inverse dynamics, which is actually like based on you can see like known values, and then you can calculate the force. Then based on that you can actually like calculate the tau based on j desired transpose to f. So then you can actually like go this, right. So after that you can see like these all the subfunctions, and I am trying to plot. Before that I am trying to you can say animate. Okay. So now in that sense if I actually like run this code, so you can see like so it is, this is the profile which is actually like given as a desired, and your system also like following it, right. So this is what you can see as a inverse dynamics in the task space, and this is the theta 1 and theta 2 how it gone based on what you call the circular profile of mu which is given, right. So now the same thing can be done in the joint space just for your benefit. So we have actually like taken that. So the inverse dynamics in the joint space. So then what happened, this was the equation. For that you need to know q double dot desired, because the q dot desired and q desired we have already calculated in the earlier code. So now we have to change. So now you can see like this way we can take it. The q double dot desired can be written as mu double dot desired minus j dot desired multiply with q dot desired. So that's why we have calculated this j dot. So now you can actually like use it. So you go back to the Matlab, and you can see I have put the that particular function as joint space. So you can see like the final equation we are directly writing in the what you call tau. So we have not calculated in f. So you can see like this is mu desired, which is actually like sorry, m mu desired has changed as m desired, then inverse of j desired that comes. So after that mu desired double dot minus j dot desired into q dot desired, right. So then these are the other effect. So now you can see the same profile what we have done in the earlier case, the same thing we have used. and you can see like this is also like following it, right. So now this is what the inverse dynamics case. So now we will go to the what you call the motion control and the model based motion control. So in this sense we will go to the computer torque control, the same code we are trying to change, only thing the initial conditions we are giving it as it is, we are not equating to the q decide first value is equal to q of first value, that is we are not doing it, we are directly using it some initial condition, and then we are adding the control parameter which is kp and kd. Okay. So now based on this, what this is the equation, if you are talking about the task space, either you can write it this way directly tau, or we can write it in this way. So we are writing in the second form. So first we derived EF, then we are actually like multiply with J transpose, that will give the tau. So that is what we are actually like writing it here. So you can see the mu tilde. So we have actually like calculated the error, mu tilde is actually like mu decide minus mu, and mu dot tilde is actually like mu dot decide minus J of J into q dot, this is nothing but mu dot, right. So then the computer torque control we have used, this is in the task space, so we can calculate EF, then based on the EF we can actually like convert it into tau. So now we can actually like go to the Matlab code. So this is we have written as CTC. So now you can see like what we have added. So this is added, right, and now you can see like this is we have commented. So we are not equating that. So now the q at t equal to 0 and q decide at equal to 0 are not equal. Similarly, q dot at equal to t equal to 0 and q dot decide at t equal to 0 also not equal. So in that sense you can see like we have just added this. So you can see like this kp mu tilde plus kd mu tilde dot as added, and we can actually like come back. So now this is actually like feed forward and feedback linearization, in addition the feedback control PD has come. So that is what we call computer torque control. So now we can actually like see so how this is actually like beneficial. Now you can see it is starting from some different initial condition and it is actually like following it. So now if you look at the error is actually like converged to 0. It started with some non-zero initial error, so that is actually like converged. So now if I actually like include this, okay, so I am just saying that the q dot and q at initial both are actually like equal to 0. So then you can actually like see, so that would actually like give much more smoother. So you can actually like see it why we are actually like saying, you can see it is actually like much more superimposed, the actual even that switching is not happening, right. So now you can see like this is in the order of 10 power minus 5, in the sense it is almost like micro level of error, right, or you can say sub millimeter level error in terms of meter if I talk, right. So now why this is required, you can see like the task space. So if I am actually like equating this, you can, I am just bringing it. So this is I am bringing it, and so this I am actually like commenting in the inverse dynamics. So you can see like this won't work as the desired manner, that is what we are actually like trying to show. In fact, it may be unstable also. You can see it is starting somewhere here, right. This is the starting point and the circle supposed to follow. You can see it is not making a circle, because the initial velocity and the final, initial velocity at desired and initial velocity actual are different, and initial position and final, initial position desired are different. So you can see it, right. So that's why I said it cannot be directly used as a control. It can be certain extent we can use a open loop control, but provided that initial conditions are supposed to match, and you can say other dimensions also make it. So now I hope you are clear why the CTC has come. So now if you want to even improve the system, even you assume that the you call the other effect is not compensated, you imagine that, okay. So now I am actually like seeing that the gravity is there, okay. So now I include the gravity, and you can see like the error may be the same order, okay. So now you can see like we have not compensated that directly, right. So that is what I want to actually like make it. So we have not compensated that gravity here anywhere. So because of that, it is actually like giving what you call this additional adverse effect, okay. So now you got idea why we need to actually like account this, right. So these all actually like additional input which you need to know. So now I'm actually like why we are actually like making it all the time gravity compensated, you would have actually like got it now clear, right? So now this is the additional you can say input which I want to give. So now we will move to the motion based control. Okay. So in that sense we are actually like going for PD and PID. So first PD with the gravity compensation we are trying to do. So in that sense the complex terms are all gone and it is just J transpose multiply with the PD and the gravity compensation. So that is what you can see, the F is added and the gravity compensation is added with this. Okay. So now we will actually like go this. Okay. So I am just showing that PD control. So now you can see like PD control, even the gravity we can include later on. So right now we can actually like see the PD control is actually like coming into a picture, right? So now you can see this is PD and the gravity compensation. In this case any of gravity is not there and you can actually like see it is starting from non-zero and it is actually like trying to follow the circle. And you can see initially there is a error, after that it is actually like much more improved. So you can actually like see there is a small error. So now if I include the gravity, we can actually like try to see so what will happen, whether this gravity is trying to compensate here or not, that we can actually like see it. So you can actually like see it thus. So you can actually like find it, right? So now the same way you can actually like see here. So the computed torque control, so you have assumed this is the initial and this decide I am not making it equal. Okay. So now I am just trying to show that the gravity is coming, but my computed torque control is actually like working or not. So you can see like this is working, but if I start from here itself, that gravity is not properly compensated. That is what the happened earlier. So now you can actually like see this is the error for this, but the PD control is actually like giving more closer result, right? So that's why I said if the gravity is compensated, if you are moving in very slow speed, even the PD control is sufficient. So that's why most of the industrial manipulator the PD control is using, but you can see like small hitch up here and there will come. This is due to what you call the constraint on the Jacobian. Okay. So now people may think the error probably further improved if I use PID control. It need not to be all the cases. So probably I will show example. So this is a PID control and we are actually like trying to show this. So now we can add at the I term and we are actually like coming back here, right? So in that sense we go to the controller directly. Okay. So the PID control and the gravity we can actually like initially ignore, then we can actually like show. So what you can see like the PID control we have actually like added Kp, Ki and so Kd is coming, right? So this is a PID and we have actually like compensated that with the gravity compensation. So I am trying to show, you can see it is not actual like a PD control performance, right? So that's why if you add the third order, you can say integral error dynamics, that may actually like end up with even deteriorate the performance. It need not to be all the time the error would be converged to 0. The error converged to 0, however you can see the dynamics is actually like modified, right? So now in order to verify that, so I am just reducing the you can say integral value. For example, I am putting it 0.5. Okay, I am just trying to show. So earlier it was 5 and now it is 0.5. You can see, so the performance is very close to PD and the integral error is actually like trying to make. So you can see it is actually like more or less closer, you can see, right? So clearly you can see. So earlier case it was actually like more converged. Now the integral is actually like making some you can say pushing different region. So now this is what I want to actually like emphasize. The PID control is not preferred most commonly in the robotic manipulator community rather than the PD, because the I term can end up with what you call wind up. So that's why we can actually like avoid this particular PID control. So now you are actually like clear. So we can actually like see further cases. If I increase the you can say PD value, or probably I can actually like add the gravity value, you can actually like see something going to happen. So now you can see like I have not changed the Ki value, but I have actually like included the gravity. So you can actually like see the performance is as similar to the earlier. It is not actually like change because the gravity is compensated, right? So now we assume that the gravity is compensated only 99%. Okay. So now the model is actually like not accurate. So now we assume that it is only 99% is gravity compensated. So you can see like it is more or less working good, but you can see like there is a error, steady state error is coming because the gravity is not completely compensated, right? So that is what the whole idea, you can see it. So now in order to make this, so if I increase I value, will it actually like make it any you can say deteriorate performance or improved performance, that we can actually like see it. Okay. So now I am actually like seeing it. So now it is actually like you can see that I is really working good, right? So that switching is actually like converge, right? So the error is actually like converge. So now if I increase the value of, you can say, the frequency, so what will happen? For example, I am increasing the frequency. So one frequency I am actually like increasing, probably this is 0.4 times. So in the sense it is actually like going to make a, you can say, 8 profile, which is very complex. So you can actually like see people usually won't do that. Okay. So I hope so it is. Okay. So I am just trying to show. So there is a error because some multiplication is missing. It is actually like not able to do because the you can say the inverse kinematics is not happening. Okay. So then what we have to see, so whether you have to actually like probably improve your control gain values. So probably I am just deteriorating this just for PD control. So I am just giving it a PD control, whether this particular performance is actually like making it or not. It is not, because it is very fast, it is actually like not able to do it. So I am just bringing it back. Okay. So I am just bringing it back. So I am trying to reduce this, that hopefully work well. I am just trying to see, so that make work. So in the sense I am trying to show a complex profile, which is actually like 8 kind of profile. I just want to show it is still, it is actually like not working because the gravity we compensated only 99%, right. So I just want to show, for that I am just assuming the gravity is a negligible amount. So I am trying to show this. So still that particular point is actually like not converge, or you can say the inverse kinematics is not happening, because this is actually like very fast, that 8 profile is actually like not making it so completely. So that is what we can actually like visible. So I am just trying to show only one thing. Okay. So in the sense I am just increasing this profile, probably this is I am trying to show probably 0.4. So I hope this will work. So in the sense I am trying to make a ellipse. So this is also like not working for us. Okay, there is an error. So because 0.8 is not possible, right. So I will just make it the ellipse the other way around. So there is you can see like I make it a ellipse. So that ellipse is actually like following it. So now I am just trying to show you can see that PD control, it is actually like converge. So now we can actually like make it this kind of complex profile or complex entity, and other things we can actually like try to do it. For example, now I assume that this is also like 0.5. So you can see like the variation is actually like completely different, right. So these all we can actually like experience and then try to do you can say different kind of simulations and all. The cascaded design we will see in the next short video, and then we can actually like go across this. So until then, see you. Thank you.